A core idea in a mathematical idea in computer graphics is the vector. And if you look up vector in Wikipedia, you'll see that there are a lot of different contexts in which it can occur in math and physics and computer science and biology and so on. We're going to be talking about the math and physics context right now. We've looked at vectors in section 1.5 in the book. The author uses vectors for collecting points for the polygon. And actually, this class is deprecated now. So in most instances, when you get code from me, you'll see vector replaced by array list or something. But this is not the kind of vector x. This is not the vector that we are talking about at this point. And for most of the course, we'll mostly be referring to this math and physics guy. We won't be talking about the physics end because we're focused more on geometry than physics, but it's a very important concept in physics too. And we'll be talking about the Euclidean vector. I'm going to give a definition of vector that I like from this book, A Vector Space Approach to Geometry by Melvin Hausner. Let's find his definition. So what he starts by talking about a directed line segment. So if you've taken geometry, you might be familiar with this kind of picture here representing a ray. So in geometry, in typical Euclidean geometry that you get in high school, you'll see this picture means we start here and go off forever in this direction. But that's not what a directed line segment is. A line segment begins at a particular point and ends at a particular point. What makes it directed is that it starts at P and goes to Q. Okay, and this will have more meaning to you as we go forward. But just keep in mind that a directed line segment has a beginning and an end. This is not the same thing as the rays that you might have seen before. And maybe the way to think about it is a displacement from P to Q. So you'll sometimes see, depending on the text, you might see vectors defined as a directed line segment. Hausner is making a distinction here because, like he would say, well, you know, this directed line segment PQ is different from this directed line segment P prime Q prime because they're in two different places in space. But vectors, if we think of these as vectors, these are actually identical vectors. And the idea is that, again, if we think of this as a displacement, we're displacing, we're moving in the same direction by the same amount in both of these. So Hausner makes an analogy. You know, we can look at two numbers, P and Q, to find a number P plus Q. And even though 3 and 7 are different from 10 and negative, from negative 1 and 11, both of them give us 10 when we add them together. So the idea is here, even though P and Q are different points in space from P prime and Q prime, if we move along the directed line segment from P to Q, we're moving in the same direction and for the same distance as if we go from P prime to Q prime. So, so basically the idea is that two directed line segments make the same vector if we have PQ parallel to P prime Q prime, and the length of PQ is equal to the length of P prime Q prime, and they have the same orientation. They're in the same, going in the same direction. So in this case, we're starting from the lower left and going, up to the right. Same thing here. Okay. So I guess the intuition for this would be if we have two vectors, and we can, you'll see vectors also given just a single name, so a single letter for a name. So we have A and A prime here. If we can take this one vector and slide it and put it exactly on top, so that they're, exactly overlapping, then they represent. We say they represent the same vector. So let's see. Oh yeah, we need to talk a little bit about this parallel business, what that means, what he's talking about with that. So because he takes it to mean something a little more inclusive. So we saw, if you've taken pretty much, even I think algebra guys have probably seen this before, that we can have lines that are parallel, coincident, or intersecting, right? If we're in two-dimensional space, those are our main choices. What Hausner is saying is he's meaning parallel to include this case and coincidence both, and you can kind of see what he's talking about. If two lines are coincident, they're moving in the same direction, right? So if we have so when he says parallel here, he's meaning that to include the case of coincidence. So two coincident directed line segments would be considered parallel. And and also there's a degenerate case here. What if we start at P and end at P? We don't really have a line, but we do consider that is considered a vector. It's considered a vector of zero length. So we kind of, for that case, we kind of have to do away with A and C here. We can't talk about a point being parallel to another point or being oriented in the same way, but they have the same length. So we do have a special case where that's called the zero vector. Let me just see, there are a couple other terms in the PDF from the MIT course. And I'm just going to talk about the geometric view here, that he talks about. So as we said, if we have arrows, if we have two directed line segments that are the same length going in the same direction, they're considered to be the same vector. There's also this term tail and head, these terms tail and head. So if you think about like the tail of a comet, that's this ending part, right? And the head is the tip. And we move in the direction from the tail to the head. Okay. What else? If we have a directed line segment or a vector that starts at P and ends at Q, we can call it PQ, where P is called the initial point and Q is the terminal point. So we do talk about that, even though, like I said, in space, you could have a P prime and a Q prime over here, but they're considered the same vector. The magnitude of a vector is denoted with these like absolute value symbols around it. And notice here we have he's using a capital letter A to denote a vector. You'll see capital letters or lowercase letters let's see, let me show you the, so a lot of times what they do in textbooks is they'll just bold the letters that stand for the vector, just because it's easier to typeset a bold than this other stuff that you'll see when you see it handwritten. So when you're looking at some of the video lectures, you'll see the professor write the U with a little arrow over it, or the zero vector will be written like this. You'll also see this little caret thing. It's called a hat. Usually we'll say the I hat for this. And that's this is also a vector. It's a special case where the vector has a length 1. So that's the basics of vectors, and then next time we'll talk about scaling and adding and subtracting.